We'll have to catch a few more miscellaneous topics from section 2.3. And by the way, I apologize in advance today. I'm pretty wiped out by allergies, so I hope I hope the video presentation goes well. So that being said, we have a few more topics to catch up here from section 2.3. None of this is really key material, but it will be on your homework. Topic 1 will be the frequency polygon. Topic 2, the time series graph. And then our third topic will demonstrate a couple of bad practices when showing graphs. Okay, a frequency polygon is very closely related to a histogram or a bar plot. So let's go back to our favorite example, number of children with these frequencies as measured by the number of families who have each number of children. We've seen this before, and we've plotted it as a bar plot. What we're going to do now basically is just connect the tops of those bars to give a linear cover to it, a shape, a linear curvilinear shape is how we would say that. And the way we graph this is this is really roundabout. We go to graph and then chart columns. In this selection, we pick the frequency column. The row labels is where the random variable is, number of children in this case. And then we are going to plot points with connected lines. That is not obvious at all, so you might want to refer to this video again if you need to plot one. But I think your homework just actually has you recognize one. All right, so when we do that, what we're seeing here is that instead of a bar that is 3 units tall, we just have a point there at height 3. And then instead of a bar that's 5 units tall, we just have a point with a height of 5. So that gives you the same basic kind of shape that we saw before. It's more or less bell-shaped, but this time is with a curvilinear cover instead of with the bars explicitly shown underneath it. Excuse me. I kind of like this topic actually because it leads in very nicely to the topic of continuous frequency distributions, which are going to be a major part of this course. And I want to make it, I want it to be very clear how this curvilinear cover is related to the bars that are supporting it underneath, even when those bars are not shown. Okay, so that's enough for the frequency polygon. Let's move on to a time series graph. A time series graph is going to look very similar to this, actually, when we graph it. The major difference is that this time our random variable will be the vertical, because the horizontal will be used for time. All right, so here's a good example of a time sequence graph, time series graph that I found online. So again, you can see in this example that time is progressing from left to right. And the random variable in this example is average sales price of houses sold for the United States in increments of 100,000 from 0 up to about 600,000. So for example, this would show you that this point represents the second quarter of 1965, at which time the median sale price was $21,000. Wow. And the most recent data point here would be, I guess, fourth quarter of 2023, at which time the median price was about 492,000. So we see that over time, in this particular example, the graph generally slopes upward to the right. And I think you know what that means. A positive slope moving upward to the right means that there is a basic trend of increasing price. If a graph goes downward to the right, that would obviously indicate a decreasing trend. And we can see a few instances of that here, basically during a recession, like this is the global financial crisis here, the Great Recession. You can see that during that time period, home values were going down pretty strongly. And there were some moments when it was relatively flat, like here in the 60s and 70s. That means basically staying constant. A huge leap here in the 2020s. So what you're basically going to be tested on is just being able to discern a trend from looking at a time series graph like this. All right, for the next couple of illustrations, we're going to basically demonstrate the principle that a graph should faithfully represent the data that it portrays. And that basically means that when numbers are to scale, the images should be similarly to scale. This is an example of Slick Sly's salary. The raw data is given over here. From the years 2000 to 2025, Sly's salary has risen from $35,000 a year, 36, 37, 38, and then it started to grow a little bit more in the 2020s, making $45,000 a year by the end of that period. If we graph that faithfully and accurately, we get a bar graph that looks something like this. I did this by hand, so it's not perfect, but it's the best I can do by hand. It's pretty good. So we have time on the horizontal axis going from the years 2000 to 25. And then on the vertical axis, we are graphing the random variable of interest, which is Sly's salary, measured in thousands of dollars. And notice that $0 is at the bottom of the scale. Salary is one of those, do you remember what kind of data that's called? It's called ratio data, because $0 truly means that you're earning no money. So since this is ratio data, that means that the heights of these bars are proportional to the amount of money earned. And we should preserve that when we graph the data. So you can see, for example, that yes, there's a bit of an upward trend, and it's accelerating a little here in the last decade. And there is a slight percentage of difference between his salary 25 years ago versus today. Now, what if Slick Sly wanted to really exaggerate this trend so that he could impress his mom or his potential girlfriend or something? What he might do is kind of choose an arbitrary cutoff point, like let's say 30,000. So he's basically going to erase all these bars down here. Resulting in a graph that looks like this. Now, these are the tips of the same bars as before, but since we have now cut off the vertical axis at a random point like 30, it basically makes this bar look 3 times as tall as that one. And that's not honest, because $45,000 is not 3 times as big as 35. So the proportions on the graph would not match the proportions in the data in this kind of an example. And the final issue, again, has to do with representations being faithful to what they really represent. And this is a tricky issue if we use areas or volumes to represent data. Technically, it's okay to do so, but if we do, the representations should scale proportionally, not linearly. Now, this concept is difficult for many students to grasp, but let me try to make it as clearly as I can. If we want to represent that one number is 3 times as large as another one, 3 times as much, and if we're using, for example, height to represent our data, then it's pretty easy and straightforward to do that. You can draw one bar that's 3 times as tall as another one. That's honest. That's really good representation. But let's suppose that we wanted to represent a value with an area instead of a height. So the issue is that if we take a square, let's just say that this represents $1. If we make this square, if we kind of multiply it times 3 in a linear fashion, in other words, if we make this square 3 times as wide and also 3 times as tall, you notice that we end up with a square that's not really 3 times as big as the original. It's 9 times as big. Do you see that? Because now each one of these represents a dollar just like that one. But if we make this square 3 times as wide and 3 times as tall, now the area of that square is really 9 times as large as the original. So it's not honest to represent a tripling in that fashion. This would really represent, I guess you would call it a non-upling. If you wanted to do that, that's fine. If you wanted to say this value is 9 times as much as that one, you can do that with area, as long as it's the area that's really 9 times as much. Likewise, if we did that with volume, this is the best example I can think of here. If we take a little cube, like this corner cube up here, you can see that the whole Rubik's Cube is 3 times as wide as that little cube, but it's also 3 times as high, and it's also 3 times as deep. So if you multiply that all out together, the volume of the whole Rubik's Cube is actually 27 times as big as the little corner cube. So if we're really using volume to represent numbers, it's okay to scale up from the small cube to the large one if you really mean to say that you're multiplying by 27. But if you're trying to say that you're multiplying by 3, then this would be very misleading because you're really producing 27 times the volume. Okay, so that's what I mean when I say that area or volume should scale proportionally. If you want to use a cube to represent your data, that's fine, but it's actually very mathematically difficult to make a cube have 3 times as much volume as another one. You'd have to multiply it by a really weird number, and that gets a little bit too sophisticated. So the simplest rule of thumb here is, let's just stick with lengths and heights to represent data. The one really major exception to this rule is a pie chart. In a pie chart, if one angle, let's say that this angle is twice as large as this one, then the area here really is twice as large as that one. So that's a case where area scales pretty faithfully. But if we try to do that with squares, it doesn't work that well. Okay, so those are the principles that end up being tested in section 2.3 for the week 2 homework.